So I want to look at position time graphs and see how they convert to velocity time graphs and then acceleration time graphs. But to get started, let's have a quick look and quick review here of position time graphs. If you look at graph number 1, so that's the top one here, this position is staying constant throughout time. So essentially what that means is the person is standing there and not moving and time's just going on. Whereas with graph number 2, what you see happening here is the position is changing, but it's changing linearly over time, or with a constant change. So that means that for every second in time, the same increment of position is happening. So for example, if this is a slope of 1, that would mean that every second that goes on, the displacement would increase by 1. So at 1 second, you'd have 1 meter displacement. At 2 seconds, you'd have 2 meter displacement, so on and so forth. So that particular displacement is constant. This one, that is to say graph number 1, has no velocity to it. There's no velocity here because there's no motion. You're just standing there. Graph 2 does have a velocity. If you recall, the slope of a displacement time graph will give us will allow us to create a velocity time graph. If I calculate the slope of this particular displacement time graph, which I already know is 1, my velocity time graph to accompany it would look like this. So if this were velocity and time, I would have a flat line here over time. And what that means is that my velocity is constant throughout time. And that should make sense. Looking back at the displacement time graph, the displacement is changing at a regular interval. Now, a little bit more complicated situation is if the displacement is not happening at a constant rate of change. That is to say, if you're accelerating. So this position time graph is a little bit more complex. It's exponential, and what that means essentially is that for every increment of time, the amount of displacement or the amount of distance covered will increase. So if we work here to create a velocity time graph from this particular displacement time graph, we'll see how that velocity changes over time. Two methods to do this. The first is to use an average velocity method. To do that, I think some of you are very familiar with the idea of the secant. So that's essentially what I would be doing here. So I can choose just 1 point if I like. So I have a data point here at 500 at 10 seconds. So that would be my first data point. My second one would be at 0, 0. And if I draw a nice straight line from point A to point B, then that will give me an average velocity over time. If you recall, average velocity is equivalent to total displacement over total time. Now, what I need to know is that because it's an average, that means that the time that I take, I have to divide that by 2. Just like finding any average, when you have 2 times, you would add them together and then divide it by 2. The same applies here. So if I use the values and find the slope of this green line that I just drew, the secant on this displacement time graph, what I'm going to do, or what I'm going to have is the slope is equivalent to rise over run, or 500 meters over minus 0 meters, so 500 meters minus 0, everything in meters, over the run, which is 10 seconds minus 0 seconds, 10 seconds minus 0 seconds. So it gives me essentially 500 over 10, or 50 meters per second. This is my average velocity. Again, the slope of a displacement time graph gives me a velocity. So this is an average velocity over time. This is the time interval from 0 seconds to 10 seconds, and because it's an average, I have to divide it by 2. That brings me to the 5-second mark. What that means is that at exactly 5 seconds, I'm traveling at a velocity of 50 meters per second. Another way of solving to get this velocity time graph is to look at the tangent method. And the tangent method is a little bit trickier because it requires essentially a finer pencil and some grid lines and whatnot, but I can give you a rough idea here. So a tangent method gives me a velocity instantaneously at many points in time. So for example, if I want to know the velocity at exactly this point here on my graph, I can draw a tangent, a small tangent line to that, find the slope of that tangent, and that would tell me the velocity at exactly that point in time. I could do the same here at the 5 second here. I could draw a tangent to that dot and find the slope of that line, and that slope should be, as we know, 50 meters per second. And as I increase in time here, let's say I'm at this point here, if I find a tangent to that, or a tangent at this point in time, all these tangents will give me instantaneous velocities that correspond to that point in time that I'm looking at. So once again, if I use an instantaneous velocity at 5 seconds, I should calculate 50 meters per second as my slope, or as the velocity. I could use the average velocity method again and use or break it up into two different points if I wish. I could, for example, find an average velocity from 0 to 5 seconds, so that would be one slope, and then from 5 to 10 seconds, and that would be another slope. And if these lines were perfectly straight, I could calculate those slopes and they would give me average velocities for the halfway point in time. For example, if I look at my first purple slope here from 0 to 5 seconds, this is looking to be a little bit messy, but from 0 to 5 seconds, the values that I have at 5 seconds are 125 meters east at 5 seconds. If I look for the slope, essentially what that means is my average velocity is going to equal 125 meters minus 0 meters for point 1 and point 2 over 5 seconds minus 0 seconds. That gives me 125 over 5, which is 25 meters per second. And when does this occur? At exactly halfway in time between 0 and 5 seconds. So at the 2.5 second mark, I would have a velocity of 25 meters per second. In other words, if I solve for an instantaneous velocity at the 2.5 second mark, it should be 25 meters per second. If I want to find another point on an average velocity time graph, I could use my two data points at 5 seconds and 10 seconds. So for that particular line, maybe I'll show you in a different color here to make it even more messy. Let's see, what kind of color can I use here? This maybe orange color. So I'm trying to solve right now for the average velocity from the 10 second to the 5 second, that beautiful straight line. The data points would be 500 meters minus 125 meters over 10 seconds minus 5 seconds. And that would give me 325 meters over 5 seconds, and therefore giving me an average velocity for that particular time frame of approximately 35 meters per second. So that's supposed to be a 35 here. 35 meters per second. Now, this time frame was between 10 seconds and 5 seconds. So when am I going exactly 35 meters per second? At smack dab in the middle of those two. So at 7.5 seconds, I would be traveling at 35 meters per second. And again, if you think about it as a tangent method, if I find the tangent, the slope of the tangent at 7.5 seconds, that would give me 35 meters per second. So in setting up my next slide here, I just realized I made a math mistake, a very simple one, but nonetheless kind of important to check this out. When I said 500 meters minus 125 meters, it should actually be 375 meters, not 325 meters. That changes our answer significantly. 375 divided by 5 is going to give us an answer of 75 meters per second. And once again, if you recall, that was at the 7.5 seconds here. So here are all the data points that I've got so far. 0, 0 at 2.5 seconds. So time here, of course, remains in seconds. I've got a velocity of 25 meters per second. At 5 seconds, I've got 50, and so on and so forth. So I'm now able, and confidently able, to create a velocity time graph. My velocity, following the same direction as my displacement, was east in meters per second. My time is in seconds, and if I draw this out here, so 0, 2.5 seconds, 5 seconds, and I think it's pretty obvious here, but this is not to scale. 7.5, 10. Let's see if I can make this a bit prettier. There we go. And then in velocities, I've got 25, 50, 75, and 100. Alright, if I plot my data points, and to the best of my ability I'll try to make this work out here. So 2.5 and 25, 5 and 50, 7.5 and 75, and you can see the pattern that would emerge. Obviously at 10 it would be 100. So what we're seeing here is a beautiful straight line going through all my points, and that is my velocity time graph. Now what does it mean? First of all, it's diagonal with a positive slope, so I know that I'm going east. It's in the positive quadrant, which means I'm going east. I've selected east as my positive frame of reference. It also means that my velocity is increasing at a constant rate. So for every second of time, my velocity is increasing by the same amount. We also know that from the velocity time graph, I can create an acceleration time graph. So if I find the slope of this particular line here, I can use basically any points that I would like. The slope's going to be the same everywhere. It's a constant straight line. So let's say that I'm going to use 5 and 50. At 5 seconds, I'm traveling at 50 meters per second. I want to create an acceleration time graph. To do so, I need to find the slope of a velocity time graph. So my points. So my acceleration is going to equal the slope of a velocity time graph. In this case, that's going to equal rise over run, so 50 meters per second minus 0 meters per second divided by 5 seconds minus 0 seconds, and I get an acceleration here of 10 meters per second squared. And it's seconds squared. If you think about just analyzing the units here, meters per second divided by seconds over 1, essentially. And we know that when we have a division of fractions, we multiply the opposite. So we flip this over, and it becomes meters times 1, and seconds times seconds, or seconds squared. And that's my unit for acceleration. So what does my acceleration time graph look like? It's pretty small. Acceleration, again, direction is east. The unit is meters per second squared. I went all the way to 10 seconds from 0 seconds, and if this is on my scale here, 10 meters per second squared, I would have a nice straight line going right across like this. What that means is that my acceleration is constant, it's not changing. It is going to be 10 meters per second. So that means that for every second of time, my velocity is increasing by 10 meters per second. Anyways, that's how you get from displacement time to velocity time to acceleration time graph.